So our topic for today is solution of regularization equation. Of course, the solution is quite involved because unlike the earlier cases where the minimization of the cost functional meant only the minimization of the square error term, in this case it is the square error term plus the smoothness or the regularizing term which also comes into play. So, I do not think that the solution of regularization equation should be possible within just one lecture, and we will be taking a couple of lectures for that. So, today in connection with the solution of regularization equation, we will be talking about Green's functions, which we will use extensively for the solution of this regularization problem. Now, in the last lecture you have seen that we had modeled the radial basis function networks as an ill-posed surface reconstruction problem. Okay. So, basically what we had shown in the last class is that the problem of the surface reconstruction which we have at our hand is not well posed. It can violate the basic properties of well posed problems, that is to say the uniqueness, the continuity, and the what is the third one? Existence. So, these three we showed that they are not being fulfilled by the functions. I mean they are not being fulfilled in practical cases when we are feeding the test patterns, okay, to the radial basis function network. So, for that matter for that matter, we also said that we will be minimizing a regularization term, and in fact the kind of equation that we had formed in the process was like this, that we got the quantity to be minimized if we write it as E of f, where f is the function, okay, which we are approximating. So, E of f, that is to say the cost function associated with this f is equal to Es of f plus lambda times Ec of f, where Es of f is the standard error term and Ec of f is the regularization term. Okay. And this lambda what we had is the regularization parameter, and EF, there is a name for this EF which we had said that it is called as the Tikhonov functional. Okay. So, we had shown in the last class that Es of f will be expressed in the standard way of half times summation of I equal to 1 to n di minus f of xi, given that we have n number of test patterns, okay, ranging from x1 to xn. So, I varying from 1 to n, that is it, and di being the corresponding desired output. So, it is di minus f of xi whole square, which is the standard error term which is there, and we sum it up for all I equal to 1 to n. Okay. So, this is the standard term, plus we had the lambda times Ec of f, which is written as half of lambda times d of f, okay, this norm of this, the squared norm of this, where d happens to be, d also in fact is a d is the differential operator. Okay. So, essentially what we have is that the regularization is to be performed. There is a smoothness term that we have introduced over here. So, if we combinedly minimized this EF, that will mean that we want to satisfy the minimization of error to the best extent possible, and also the also imparting the smoothness to it to the best extent possible. So, we have to solve these two together, because these term added to this, okay, actually forms our functional to be minimized. Now, I mean, up till there we discussed in the last class itself, but there are one or two points that is worth noting. You see that in this equation, if we make lambda tending to 0, okay, that means what? That if I make lambda tending to 0, make this lambda very small, in that case EF can be approximated by ES of f. In fact, that is what we have been seeing all throughout. I mean, for the case of the single layer perceptron as well as for the multi-layer perceptron, whenever we were taking the cost functional, we were always taking the standard error term square. So, lambda tending to 0 obviously puts the restriction onto the data space that we have got, okay, and with lambda tending to 0, it does not give any importance, any significant importance to the smoothness condition. It said that, okay, I mean, whatever data is supplied, okay, I do not care whether it is smooth or not, okay, whether the data contains noise or not, you have to pass a surface, okay, which should be such that the standard error term is minimized. Whereas the other extreme, okay, could be that we make this term lambda very high. Okay, let us say theoretically we make lambda tending to infinite. If we do that, then we can see from this equation that by that process we make the importance of the first term, that is the standard error term, less, and we are putting too much of importance to the second one, that is to say to the regularization term, which means to say that as if we are trying to say that the data set that is given to you is unreliable. So, what you simply do is that you simply interpolate a functional, okay, where the smoothness criteria is absolutely fulfilled, where the smoothness is there and where the minimization of this differential term takes place. Okay. So, these two are the extremes, that either we put too much of importance to the given data or we do not put any importance to the given data at all. So, in practice this lambda that we have got should be somewhere in between these two. Okay. I mean, it should not be very low, okay, just to make the regularization term insignificant. It should not be very high just to make the given data set unreliable. So, we have to make a balance of these two. Anyway, I mean, given that this kind of a functional exists with us, that is to say, given that the Tikhonov functional is the one that we are trying to solve, okay, naturally the thing that we have to do is to determine that what is the best functional f, right. Our problem at hand is to determine the best functional f, okay, which minimizes this Tikhonov functional E of f. That is what our aim should be, right. So, the question is that if we have to do that, then surely we have to find out that what is the differential of these EF terms, okay, and we have to minimize that differential, right. So, what we do is that in order to solve this equation, okay, we first formulate this problem in terms of differential, which we are calling as the Freckett differential. So, we are introducing the Freckett differential. So, we are going to write it in the form of Freckett differential of Tikhonov functional. And let me explain what this Freckett differential essentially means. Okay. Now, just let us go back to the theory of the elementary calculus, where you have seen that I mean, if we have to, I mean, if we have got a curve, okay, and if we want to determine the local value of the curve at a given point, what do? Then we consider the tangent to the curve at that particular point where we would like to find out the value of that differential, or to I mean have an infinitesimal linear segment of the curve there. So, the local value of the curve at that point will be determined by the tangent at that point. And likewise, the local linear approximation to the Tikhonov functional will be given by, I mean, we can write the Frecht differential's definition as the differential written as d of E, okay. And in fact, the arguments to this we are writing not only f, but another term, okay, another function which we are writing as h, okay. And what is this h will be clear to you very shortly. So, we are going to write this differential, Frecht differential, as d beta, okay, where we introduce a new variable beta, okay, and we take the differential or the derivative of the functional e of f plus beta h. Okay. Now, e of f we know. So, what we are simply doing is that we are taking e of f plus beta h and we are taking a derivative of this with respect to beta, okay. And this derivative we have to compute at beta is equal to 0, and if we compute that, then this is the local linear approximation. So, this what I have written just now is the local linear approximation to Tikhonov functional. Right. So, here actually this h of x, what we have written, this h function that we have introduced over here is a fixed function of the vector h. Of the vector x, right. So, what we have as the necessary condition for the functional f of x to be a relative extremum of EF. I mean, because after all what we are going to do is that we are going to find an extremum of this EF functional, right. So, the necessary condition for that is that d, that is the differential E expressed as arguments f comma h, should be equal to the differential des of f comma h, okay, plus lambda times dec f comma h. You understand that this is very clear that we are writing the old equation only, that is to say EF is equal to ESF plus lambda ECF. This equation we are simply going to rewrite in terms of its local differentials, okay. And the local differentials are DEF for this one, DES for this one, and DEC for this one. So, it is DEF is equal to DES plus lambda times DEC. And this differential, I mean, since we have to find out the fx, which has to be an extremum of the functional fx, okay, extremum of the functional EF. So, for we can say that for f of x, okay, to be a relative extremum of the functional EF, okay, then the condition that we have to import is that this DEF is equal to expressed as a summation of this, that should be equal to 0, okay, because we want the extremum, we want it to reach the extremum of EF, okay, when we want to minimize this. So, now what we can do is that now that we have got two terms ES, or rather the differential DES and the differential DEC, okay, we can attempt to now solve for this DES and DEC separately. We can write down the corresponding differential expression for that, because ES we know very well that ES is expressible by this equation, that is to say half times summation I is equal to 1 to n di minus f of x I, okay, this whole square. So, this is the expression for Es of f. Now, of course, what we have got is Es of f comma h. That means to say that we have got to find out the derivative of Es of f plus beta h. So, just to write it down, des f h by applying the same definition. I mean, Frecht differential definition if we write down now for Es. Okay, that is to say for this, if we write down Frecht differential expression, then that will be as before, that can be written as d beta of Es f plus beta h, okay, for beta equal to 0. Okay. Now, Es f plus beta h. Now, Es is what? Es is di minus fxi. Okay. So, if I write Es f plus beta h, in that case it will be di minus fxi minus beta h xi. Sure? Means instead of fxi, it will be fxi plus beta h xi, okay, written in this form. So, we can simply write down this as half, okay, half obviously coming from here, okay, this half term I mean to say, half into d beta, okay. So, the half can be taken out of this whole expression, half d beta, and now introducing the summation that we have got for I equal to 1 to n, and then the error functional. Now, the error functional will be in this case di minus fxi, and not only fxi, because now the argument is f plus beta h. So, that is why it is fxi minus beta h xi, right, this thing square, okay, which we have to calculate at beta equal to 0. H is some function. H is a fixed function of the vector x. We have already said that. Okay, right? Square will be inside the bracket. Yeah, there is one more bracket. Yes, yes, yes. You are very correct. Yeah, there is one more bracket. Is it right? Yeah, right. Because this this square bracket was corresponding to the summation terms. I mean this terms argument. That is the error terms square bracket ended here. We are taking the square of that, and then this square bracket is for the overall term. Okay, and there we have to compute it for beta equal to 0. So, what is the meaning of fixed function? Fixed function, you see, that is to say, I mean this is from the theory of calculus itself, that what we are doing is that we are finding at this point f, okay, we are finding the value of f plus beta h. That means to say that we are going to an incremental step of beta, okay, and h is a functional there, I mean h is a fixed function there. So, what we are doing is that just like the way whenever you are trying to find out the functional value of a curve, okay, at a point beta, what you do, I mean f of x you are going to find out, you are going to find out f of x plus h beta, okay. I mean very similar way, I mean in this case you are not doing it for the curve, you are doing it in the vector space. So, that is the purpose of this fixed function, and now I mean it is just written in this form. So, I think up to this we do not have any problem. So, simply it can be simplified further. As a matter of fact, that if we take the d beta of this, if we differentiate this with respect to beta, then things will turn out to be pretty simple. Okay. What we will be getting there is that, I mean if I write down, then you can verify that later on. Okay. This becomes equal to minus of I equal to 1 to n. This half term obviously goes out, because once we are differentiating with respect to beta, because there is a square term over here, okay, this half term gets cancelled in the process, and this becomes a formula like this, summation of di minus f of xi minus beta h xi, okay, and this we have to multiply by h of xi, very correct. This has to be multiplied by h of xi, okay, and this we have to compute at beta equal to 0. Now, this is very clear that why h of xi will come, because you see that there will be in fact a term which is associated with this h. So, there is beta h term. So, obviously, what we have to do is that it is square of this and differentiated with respect to beta. So, this obviously will mean that there is an h xi term which also comes, and now computing this for beta is equal to 0 is pretty simple. What simply we do is that in this expression, if we put beta is equal to 0, then what results is simply minus summation of I equal to 1 to n, okay, di minus f of xi, okay, multiply by h of xi, very correct. Okay. So, this is a good form that we have got, that is to say the computation of DES FH. All right. Now, this in fact, I mean if you look at it, this is going to be what? Okay, this, I mean, is this a vector or a scalar? This incidentally happens to be a scalar quantity, okay, because di is a scalar quantity if the function is a scalar ultimately, okay, and h of xi. So, here this can be represented simply, I mean this product that we have got, it can be represented as inner product of two quantities, okay, and to express it that way we are making use of a theorem which is called as the Rise representation theorem. Rise representation theorem, and what that means is that let f be a bounded linear functional in Hilbert space, okay. Let f be a bounded function in Hilbert space. And what is Hilbert space? Hilbert space means that for which the inner product space that is complete, okay. So, the inner product space that is complete. So, and we are denoting it by H, the Hilbert space is denoted by H, okay. Then it says that there exists one H0 belonging to this H space, all right, such that f can be represented as H comma H0, okay, in Hilbert space H for all H belonging to Hilbert space H, okay. So, that means to say, okay, I mean let us not get very much confused with this terminology. This term H comma H0, what is simply written is the inner product in the Hilbert space. So, what it means to say is that this function f that we have got is expressible as an inner product of these two functions H and H0, okay, which exists in the Hilbert space. So, we are just going to write the functional as an inner product in its Hilbert space H comma H0. So, if as the function we take this differential DES in this expression, if we go back to this expression and try to apply this Rise representation theorem, then this DES for us should be expressible as what? As an inner product of H and this summation term, okay. In fact, I mean in terms of this Rise representation theorem, the Frecht differential of this DES term, okay, can be rewritten as follows. So, in light of Rice representation. Okay. It is possible for us to write DES f comma h is equal to minus, here minus is there obviously, and this is a product of these two. So, we are just expressing it as a dot product. So, this can be in the Hilbert space written as h comma summation I is equal to 1 to n di minus f. We are not writing f x I again and again. So, it is di minus f, and what we have to do is that we have to write it as this times delta xi, okay, where delta xi is the direct delta. Okay. In fact, this inner product is written in the H space, in the Hilbert space, all right, and here this delta xi what we have got, okay, of this x, this is equal to delta of x minus xi, okay. This is the direct delta distribution of x vector. X vector centered at xi. Right. So, this must say what, that only when this x vector is equal to xi vector, in that case the direct delta is equal to 1, and otherwise, I mean, when xi vector is not equal to x vector, then that is equal to 0. So, it is the direct delta distribution definition directly. So, in terms of this, okay, this term of the Freck differential of DES is represented as an inner product of these two in the H space, that is the Hilbert space. And and now let us go over to the second term of this, because this was the way we represented DES, and now we have to represent the next term, that is DEC. Okay. So, to represent DEC, we should follow a similar approach. In fact, DEC, by applying the definition of the Freck differential directly, where DEF is equal to d d beta of this, if we have to compute DEC of f comma h, it has to be d d beta of EC of f plus beta h computed at beta equal to 0. Okay. And then we will make use of the expression for EC that we have got. In fact, expression for EC is this term, I mean half of norm of df square. This is the term that we had got as a definition for this ECF, that is to say the regularization term. So, now to find out the Freck differential of the regularization term, we proceed as follows. So, the evaluation of Freck differential for the regularization term gives us DEC of f comma h should be equal to d d beta of EC f plus beta h. Okay. And this is to be evaluated at beta equal to 0, which means to say that this is equal to half of d d beta. Okay. Now, we apply the definition of this EC, and what is the definition of the EC that leads to? Okay. What we have to do is simply take the, I mean this is, we said that it is d f, I mean the differential of this f. In fact, this differential is in the multi-dimensional space. Okay. So, this is the multi-dimensional differential operator that we are taking over this f. Okay. Then this is wrong. I mean, I should not say df vector. This is d is a vector quantity, no doubt, because it's multi-dimensional differential operator. So here, in fact, for this thing, d d beta of EC this could be written as half of d d beta instead of EC. Okay, we can express it as an integral that is defined in the M0 dimensional real space. Okay, the input, I mean there are M0 number of inputs. So, naturally the input space itself is M0 directional. So, what we have got following the definition of EC itself, that it can be written as the differential of f plus beta h, this argument f plus beta h, and we have to say this argument square of this, okay, differential of this f plus beta h whole square. This is from the definition of EC itself that we have got, and we have to integrate this in the multi-dimensional X space, okay, or Rm0 space. Okay. So, this times dx, and we have to add it over the we have to integrate it over Rm0 space, and of course, everything to be computed at beta equal to 0. Again, we have a half term over here, and within this we have got a differential with a square term. Okay. So, in effect these ultimately cancel out, and what we get as a simplification to this expression, this I mean Frecht differential definition of this regularization term, okay, that leads us to, this can be written, I mean that is to say the dEc of fh, f comma h, this can be written as the integral over this Rm0 space, okay, of d f plus beta h, okay, and we are going to have, okay, in fact d with the vector sign that we need to do, and here this times dh, okay, this is coming from the differential itself because we are taking that, and this dh dx, okay, and this we have to compute at beta is equal to 0. So, which means to say that this argument which is now f plus beta h, that will become f. So, this simplifies further to Rm0 integral d of f times d of h dx, okay, and this integral, okay, is one and the same as writing that in Hilbert space we could express it as the inner product dh comma df, okay, in H space, and we can call this as the equation number 1, let us say. Okay. So, what we did so far, okay, again I mean so that to keep you in tune with what we have been doing, again we have taken the, I mean we have resorted to the calculation of this dE of fh, the differential of the Tikhonov functional, expressed this as a summation of these two, and individually this dEs and dEc we have expressed, and the form which we chose in order to express that is the inner product form. So, Es of fh, okay, has been expressed as the inner product form like this. Okay. In fact, let us call this as equation number 1, okay, because this equation will be of use to us. Okay. And the second one, that is to say dEc, what we have got at the end, dEc of f comma h, okay, this to be equation number 2. All right. So, these two are quite important to us, and based on these two very important relation, okay, we will now go further to have a, I mean first we need to have a proper representation of the equation, of the regularization equation in the differential form, and then only we will try to solve that. Yes, please. Any questions at this stage?
From that step, can you show the previous slide, sir? Previous.
This one?
From this step, the half
Yeah.
we get I think 2 beta d hx square, sir, and the other term. So after this,
Yeah. Here.
yeah, from this to this you've come from that place to second yes, this place to this.
From here to here.
I think there will be a term of beta square d square h. Acha, beta is 0.
No, no. Beta is 0. Beta is 0. Anyway, I mean this you can verify. I mean this this is an established result. So I think I mean with a bit of I mean manipulation or with the differential computation we can get it. I mean it's not difficult to get one. So this is the differential form that we get. This is an established equation. So yeah.
Sir, if this integral has come in DECFH1, you have defined, sir, that in the over the dimension Rm0, so you have integrated it. Previous
1 minute. This one?
just previous to this.
Oh yeah, I was taking a different.
This one only.
Yeah, right.
This integral, sir, how this has come?
Yeah, you see, what we are doing is that what is EC's definition? EC's definition says that it is differential of f. Now we are computing the differential equation, differential of that at the point beta equal to 0. So what we have to do is to consider the function not as f but as f plus beta h, okay, with beta is equal to 0. I mean, so we have to consider the function there. So it is the differential of that squared, okay. Now this differential that we are computing, this d of this square that we are getting is in the I mean this is in the unit input space. So what we have to do is to take the differential of the input space, okay, which is given by this dx, okay, and then integrate it over the input space itself. This Rm0 is the input space directly. So that is how we got this overall integral term, okay. And then what we are getting is this d beta term, okay, that goes out for us, okay. I mean, in fact, just a minute, why are you saying that there will be a beta square term out there? I think beta square. Huh?
Beta is 0, that side is 0, otherwise.
Yeah, beta is 0. So ultimately we are getting this result. Yeah, so dH dF, so inner product of that. So that is important. So we have got DES and DEC both representable in the inner product form, okay. Now yes, our objective is to write this differential in a manageable form. I mean, first of all, that we haven't been yet able to write it down. I mean, our functional minimization that we are going to achieve, okay, is not yet written in a manageable way. So we are going to write it in a more manageable way, and for that we make use of a popular equation which is called as the Euler-Lagrange equation. And what does the Euler-Lagrange equation has to tell for us? That is to say that given a linear differential operator D, we can find uniquely an adjoint operator D, we can write it as D tilde, we call this as adjoint operator D tilde, okay, such that for any pair of functions, we take a pair of functions, let us say the functions that we take are ux vector and vx vector, okay, which are differentiable and satisfy proper boundary conditions. Okay. Then we can write integral over Rm0 space ux vector d of vx vector. Okay. We take two functions, okay, pair of functions ux and vx. What property does it have to fulfill? You will see that ux times differential of dvx, okay, in dx is equal to integral over Rm0 space vx d tilde of ux, okay, dx. So, you see, just note the rhythm of this equation. You see here ux is there and the vx is associated with the differential operator d. It is the derivative of v, okay, and this is equivalently represented as, you can write it as vx and take the differential of ux, but not the exact differential. You take the, what you call as, I mean, you can treat it as an inverse differential kind of thing. I mean, this is d tilde, I mean, it is called as the adjoint operator. In fact, this is the way of defining the adjoint operator in terms of the differential, and in fact, it is, I mean, if you are treating the d, the operator d as a matrix form, in the matrix form if you treat the operator d, then d tilde essentially means the transpose of that matrix, okay. D tilde effectively becomes the transpose of that matrix. So, ux dvx written in equivalent form as vx d tilde ux. So, I mean, it has got, I mean, analogically in matrix analogy, it is like, I mean, this d operator is, I mean, this d tilde operator is just like an inverse operator that is happening, okay. Now, this equation, okay, is a very popular one, okay. In fact, this is called as Green's identity, okay. So, this is known as Green's identity. So, please remember this. So, those who have taken a course on this, okay, I mean, on the partial differential equations, etc., okay, must have come across this Green's identity, okay. This is a very popular one where it is expressible this way, okay. Now, we can, I mean, let us see that if we can use the Green's identity to our best use here or not, okay. Now, all right, let us have a look at the differential that we had got for EC. The differential that we had got for EC simply said, yes, that is the one, dECFH is equal to integral over Rm0 space, of course, df dh, okay. Now, df dh means that if we want to write it in the form of the left hand side of Green's identity, you see, now I am putting these two equation, okay, together. The left hand side of Green's identity ux dvx dx, and now look at this dEC. dEC says df dh dx, as if to say that h here plays the role of v, or rather to say d of dh plays the role of dv, okay, and in that case ux here plays the role of df, right. So, now from this two things, I mean, that means to say if I call this as equation number 3. Okay, Green's identity if I call as equation number 3, then comparing equation number 2 and equation number 3, okay, comparing equations 2 and 3, what we get, ux is equal to d f of x, okay, and d v of x is equal to d h of x. So, if I can draw an equivalence from the left hand side of Green's identity, then I can express this in terms of the right hand side of Green's identity. And what does the right hand side of Green's identity say? Vx, and what is Vx in my case? H of x. Okay. So, this can be written as, rather to say, dEc of Fh, okay, can be written in terms of Green's identity as Rm0. Yes, please, I mean, please dictate to me, then only I will know that you have understood this. H of x, yes, d tilde d of fx, right. Why d tilde? Because it is to be expressed as d tilde ux, and what is ux? Ux in our case is df. So, it is d tilde df. Okay. So, it is hx d tilde df of x, right, dx. Okay. Very good. So, this is equivalently in the inner product form. It is expressible as h comma d tilde df in Hilbert space H, right. So, that is it. And now, if we return to the extremum condition, in fact, this is nothing but the representation of dEc of Fh, okay, in a different way. I mean, we earlier expressed it as the inner product form only, but it was dH comma df, and now we are writing it as h d tilde df, that form, okay, in the Hilbert space. Now, since this is the representation of EC, okay, we can equivalently now find out the differential. Now, I mean, our aim is to find out the differential of E, okay, not the differential of ES and EC alone. So, we have already got the differential of ES and EC, and what we now have to do is to add this ES and EC terms together. Okay. In fact, the addition is of course through the use of this lambda, all right. It is dE is equal to dEs plus lambda dEc. Okay. One and the same as saying that it is, if I say 1 upon lambda dEs Fh plus dEc f comma h. Okay. I mean, we can say that lambda is not equal to 0. I mean, in that case it is possible for us to write it as dEc plus 1 upon lambda dEs, and if we do that, then the dEfh, okay, can be combinedly represented as the inner product form as follows. So, a combined representation of dEfh in the inner product form is given by this: dE f comma h is equal to h comma, okay, we have d tilde df. Okay. Now, this d tilde df we can very easily recognize that this d tilde df is coming because of our regularization term. The regularization term here, that is the EC term, is contributing to d tilde df. Okay. So, h comma d tilde df, but here we do not have, not only, I mean, we have not only the regularization term, but also the standard error term, and standard error term also has been expressed equivalently as a as an inner product. So, what is it that we had got? We had got there as inner product, look at the expression h comma this, h comma summation this. So, we have to write it as minus 1 upon lambda of this, okay, h comma 1 upon lambda of this. So, effectively it is d df minus 1 upon lambda summation I equal to 1 to n di minus f, okay, delta xi, again delta xi is already defined, it is the direct delta, and it is inner product of h with this term, and this term takes care of both. This d tilde df takes care of the EC term, and 1 upon delta of this takes care of the standard error term, okay. And together, I mean, for both we have got it as inner product with h. So, combinedly as inner product of h, it is h comma this. So, this whole thing should be an inner product in the Hilbert space, all right. Now, what we have to do is that the Frecht differential DEFH, okay, is 0 for every, I mean, since we are looking for the extremum of this term has to be 0, this differential is 0 for every h of x in H space, okay. So, we can write that the Frecht differential dE of fh, okay, is 0 for every h in Hilbert space if and only if, what is the condition? If for every h it has to fulfill, what should be the condition to make DEFH equal to 0? This is already written in the inner product form. That means to say that the second term which we have got as the inner product expression has to be equated to 0 simply, okay. So, simply we have to write it down as d tilde df, okay, is equal to, I mean, minus this is equal to 0 means as if to say that we have got that equivalently d tilde df of x equal to 1 upon lambda summation I equal to 1 to n, okay, di minus f of xi, okay, times delta xi means it is delta x minus xi, all right. And in fact, here we are writing it as f, and what is this f? This f is the f that we are looking for, that is the f at the extremum, because only at the extremum we are equating dE to 0, right. So, at the extremum we are writing it as f lambda, okay. So, where f lambda is the extremum value, so f lambda of x is the extremum value. Now, what have we got? We have expressed now the functional, okay, in terms of this equation, but we have to now solve for f of lambda, okay, which is still not very easy, because this involves the derivative terms, differential terms are involved associated with this. So, what we have to do is to solve it using integral transform methods, okay. And we do not have time to cover that, although the title of the lecture said that I wanted to introduce Green's function. Ultimately, I could not because of the shortage of time for today. So, in the next class I will be introducing the Green's function, which will be needed for us to solve this regularization equation, okay. Thank you very much.